Hi, good afternoon. So I don't know, this is maybe the first SNC work, and most of the previous talks were deterministic network calculus. So I'm going to talk about modeling and performance analysis of heterogeneous sync tree networks, just to motivate why do we need to study this. So most of modern networks are actually a mixture of wireless access and wired backbone networks. And especially with the advent of the CPS, machine type communication, so the performance become crucial, and we need to study that performance, especially in industrial applications. And most of the studies, like in the literature, usually that study wireless systems, they don't care about the wired part. So one important example in industrial application is the process monitoring and automation. They usually use like wireless sensor, deploy wireless sensors where in places where the wired connectivity is not possible. And then basically all these sensors will provide some measurements. These measurements will be collected. It could be video, it could be other measurements, and it will be collected by a wired network and forwarded to a sink. And that sink might by itself be a processing node, or maybe it's just forwarded somewhere else to be processed. So the function of the router in this case is to route all these information towards the sink. And in this way, we're going to get basically a sync tree. Okay, so that's why we have the heterogeneous part is because we have the wired and the wireless, and the sync tree because of this topology. So this is what motivated our study, and we are using stochastic network calculus to do this analysis. So to jump right into it, so basically this is the model that we have here. So basically we have traffic sources, and then we are assuming each one has it's a wirelessly connected, basically to through access point. And then we will have a backbone network, which we can model by a sync tree. And then it basically goes to the root node, which is the here, the destination. These are like some simple assumption. We model this as this sync tree here. And we have M layers, basically. And each layer, each node, except of course for layer 1, have 8 children. We are assuming the arrival is regulated by leaky bucket here. And for the wired part, we are assuming rate latency servers. And for the wired, the fading channel, we are assuming an independent point-to-point Rayleigh block fading channels. And the channel, the service. Yeah, and the service, the instantaneous service is actually equal to the channel capacity, the Shannon channel capacity here. Gamma sub I of V here is the instantaneous SNR, which is for Rayleigh block fading. It's exponentially distributed with mean value average SNR gamma bar. Okay, so to analyze this, I'm going to take like a page from Paul's presentation area. So we're going to go with pay multiplexing only once. It's recently applied to stochastic network calculus by the paper just presented half an hour ago or an hour ago. And then basically what it does here is that we compute a residual service for us, flow 1, by basically each flow passes through some path here, which we call pi sub I, and the length of the path is L sub I. And what we do here is that we assign an order set of time variables at the input and output of each server in the path. And then the next step is basically to sum up all the servers over the period of the time variable that's associated to its input and the time variable that is between these two, associated to its output, and then subtract all the traffic on the periods where the time variable that is associated with at the point when it joins the network, and the other delimiter would be the time variable at the point where it exits that variable. So, I mean, visually, you can very simply, you can compute this. And I'm going to show you an example here later on how to compute this. And then you optimize over all the set of these ordered time variables. Okay, so, and according to the presentation earlier by Paul, this reduced the gaps between simulation and SNC significantly, and it compares favorably from computational wise. And then it also applies to trees, which is important for our application. So a simple example, if we have this two-layer tree example, and we want to apply this, so the first thing that we do is basically allocate these time variables. And you can see that at each entrance and exit of each server, we have a time variable. So we'll have, for flow 1, we have T1, T3, and T4. And for flow 2 and 3, we have T2 and T3. And then for flow 2, T3 and T4, right? So, and then here we just basically, we compute for flow 1, we can compute a residual service curve in terms of summing all the servers in the network, the 3 servers here, and then subtracting the other flows, basically the F2 and F3. And as you see, for F2, it joins at T2 and exits at T4, while A3 joins at T2 and exits at T3. Okay, and then we optimize over all these, over the union of all these events, all these time variables, ordered time variables. Now, applying this to our sync tree here, we can obtain this residual service, end-to-end service curve for any given server J. Note that in our case, all the flows are joining at their respective at the entry point in the network at first layer, layer 1, and exit at the last layer, which is the root. So that's why we have here TI1. TI represents for every I that from 1 to n, these are n flows. So it goes from T1, T2 up to Tn, comma I, and exits at the output of the root, right? So we subtract all these flows except for the one that we are interested in, which is J. And then we add up all the servers. And here you see for each server, this time variable is associated to the specific, to the entrance of the specific server, the input. And then this is the successor in the next layer, right? So, and then we optimize this over all these time variables. Basically, these are the ordered time variables. So TIK, and this guy is the successor of TIK in the next layer. Okay. Now, if we have a rate latency servers at the layer 2, as we assumed for layer 2, 3, 4 upwards, we can sharpen this even further by subtracting the latency here. Since we have for rate latency server, there is no service offered for V greater than T minus uppercase T for that latency, for that period. There is no service offered. So we can reduce the set even further by subtracting that. Now, so we have this. Now, how do we compute the performance bound? So let's take basically the backlog. So now with the backlog, the violation probability of the backlog for a given backlog bound B is bounded by the probability that the deconvolution of A1 and the end-to-end service that we just computed is greater or equal B, right? Sorry. Yeah. Okay. So now what we can do is basically substitute the service curve that we computed earlier here. And then we can use basically Boole's inequality. But then we have to apply it once per optimization. And we know that Boole's inequality actually, or the union bound, is a major contributor to the slackness of the bounds, right? So what do we want to do? We want to reduce the use of the union bound as much as we can. And a better approach that we are trying to do is basically to utilize the deterministic nature of layer 2 up to layer n, because we have the random part is only in layer 1 due to the wireless links. The other layers are actually deterministic, right? So, and this way maybe we can reduce the use of the pulsing quality. So first, to do that, what we can do is basically partition the network and isolate the deterministic part and optimize it separately. And then we try to apply the dupsing quality whenever it's possible instead of the union bound, because dupsing quality is proven to be tighter than the pulsing quality. And then we can also study some behavioral trends, maybe that can help us improve the bound further, apply some of the techniques that's already in the literature, like the edge mitigator, to further enhance the bound. So the goal here is to get the tightest bound that we can with the available tools. Now, so to do that, to compute the end-to-end service this way, the way we described, so what do? We partition the set of all nodes into 3 sets. So all these calligraphy letters are actually subsets. So we have W for the set of flows and the wireless node, because we have 1 flow per node by assumption, so it's the same. And then we have the set N, which is the set of wired nodes. And we also define a set L, which is the wired nodes in layer 2. This is the interface between the wireless and the wired part of the network. So we need that. We will see later why. Okay, and we also, for each flow, we define pi I, which is basically the path that flow I takes from 1 to m, because as I said, all the flows enters at layer 1 and leaves the root. So it takes m hops to get to that point. Okay, now based on that, we can compute an end-to-end service, residual service for flow 1 in terms of basically this is the SI is all the nodes in the first layer, the wireless node. This is I in the set W, and then we'll have also the servers in the rest of the network, which is the wired part, which we call the set N. Okay, so now this we separated. The only thing that is common between them is this is the successor of I. Basically, it's in layer in L, in the set L, and TJ here is also might be in set L. So what we do is basically by fixing this TJ, in this case for all J in L, then we separated the 2 parts. Then we can optimize the deterministic part independently this way. Okay, so let's do that. So this theorem basically it computes a service curve, residual service curve, end-to-end service curve for the deterministic part, right? And this is the part that we isolated earlier. And then this is given by this sum. Now here, what R sub j is actually R sub j is the minimum of Rj or the sum of its children, except if it's in L, then it's the same as Rj, right? So if it's in the set L, so the first layer, the first deterministic layer, then R sub j equal Rj. For the other layers, what we do is we take the minimum of Rj and the sum of all its children, the rate of all its children, right? R is the rate. And for the time variables here that we are used, V sub j. So if j is in L, then Vj equal Tj, it's the same time variable. However, for other layers, what we do is we take the maximum. So this is recursive, as you can see. The maximum V sub h, h is one of the children, predecessor of j. So one of the predecessor of j is the set of all children of J. So we find the one that maximizes VH, and VH can be computed with its children, so on, and until layer L. And then we add the latency for that server. Okay, so in this case, we are assuming T0 to be the associated with the output of the root, the output at the end, which we fix, and then we let V0 equal T0. Okay. Now let's take a simple example and see how this can be applied. Okay, so I'm taking this 3-layer symmetrical binary sync tree. Basically, what we have here, this is the deterministic part, and this is the wireless link, which is the stochastic part. So 1 and 2 will be in L, 1 and 2 and 3 will be in N, right? And these 4 servers will be in W, right? In the set W. Now we are assuming symmetrical, just to make life simpler for now for this example. So we have R1 equal R2, T1 equal T2. So for each layer, what we mean symmetrical, each layer would have the same parameters for the servers in that layer. Okay. Now we use the theorem 1 that we use this theorem here, and we apply it to obtain the service process for the deterministic part, as you can see. So we have basically R sub 1 is this one, which is equal to R1 because it's in L, and R2 the same thing. R2 is in L, so R sub 2 equal to R2, which is equal to R1. So that's why we have R1 here. And R3 would equal to the minimum of R sub 3, minimum of R sub 3, and the sum of the two, which is 2R1. 2 sub R1, right? So it's the minimum of R3 and 2 R1. And for the time variables, we do the same thing as we described there. So basically, V3 would be the maximum of T1 and T2. Here we have V3. V3 would be the maximum of these two minus minus T1, and it's minus T1 plus T1, then it will cancel T1 with T1. Okay. And then we have, the same thing here, we apply here, and then we will end up with this backlog bound. I'm getting time crunched, so I'm going to go quickly. Okay, so now what we do is we can basically by applying this into applying theorem 1, and then to get the deterministic part service curve, which is already optimized. So we already reduce the number of the application of union bound, and then what we will end up with is we can separate these two parts, as you can see here. So we have, this is the deterministic part, and this what remains. Basically, S is the wireless capacity for wireless links. And then we can do some rearranging and separate this, take it to the right-hand side. So all this is deterministic on the right-hand side. And we end up with this random variable xi of t successor of I. And we can use the union bound for these successors of I. So these are the in L, the servers in L. So we only need to do that many union bounds, right? And then xi is defined as this supremum. Rho I, basically, as we said, the arrival is regulated. So this is rho I, t minus u, minus the service. And then all what we need is to compute this probability. So if we call this all y, then we need to compute the probability that the sum of xi greater than y. And we do martingale analysis for this. So basically wi, because si is S sub I is IID, then we can just construct a martingale, a backward martingale, and then apply results already available in the literature. Then to compute a bound, and then this xi, which is the supremum of wi, will be bounded by some exponential function. e to minus theta I y. Now what we can do, we need to compute the sum of these xi's greater than some y. And to do that, we also have some results there. This theorem, basically what we use the dominant part, the dominant term here, and then we can simplify it further if we assume symmetrical tree. Some results. I'm gonna just, I know you're, I'm just gonna go quickly. Okay, so we can see here, these are the, what we have is this is the original bound, and this is the simplified bound. So we 1 and 2, and by applying this, no way. Okay, so for the first part, as we can see, it's already basically optimized. It goes to with theta. So theta 1 is optimal at theta star. This is theta star, which is, in this case, we are using gamma bar 20 dB and rho 3.5. Gamma star, theta star would be around 0.69. And then this is for different values of y. And if we use the simplified one, we need to optimize, as we can see, we need to optimize for every different value of y, which basically for every different term in the sum eventually, we need to optimize that because they give a different optimal value. This is if we only compute, we are comparing if we are computing 50 terms, 50 first term versus 5 first term. And the one on the top, there is no difference between 50 or 5, which means the dominant terms already. Yeah, okay. Okay, and this is basically the backlog. And yeah, for these parameters. So we see that the application of local martingale actually improves. It's almost 50% at high utilization here. This is the PMO. And then we applied also the H mitigator, and we can see we can still get some gain. But then the other line, which is very close to this, is when we compute only the first 100 terms using the original formula. So it only can be computed numerically. We cannot, we don't have a closed form there. So we can see we can get very close to that. Okay, and yeah, so this is what we did. We studied the performance of the heterogeneous network, and we utilized different techniques available in the literature, and we try to minimize the use of the union bound by using dupes inequality in some cases. And then we got some good results, some enhancement. Yeah, and that's it. Thank you so much, and sorry.
Thank you very much. Yeah, I mean, it's difficult to give that much technical detail in 20 minutes, 25 minutes. Thank you, Hussein. Do you have a question? Yes.
I have a short one, a quick one. I think on slide 13, you had one.
Which slide?
13.
13.
Yeah, the first line.
Yes. Okay, if I tell you, I have to kill you. No, sorry. So, yeah. So this is basically something from what they did in Paul's paper, basically. So what we do here for x sub k, we can compute an MGF bound, and then use the generating function to get a bound on that on the sum of the MGF, and then we can compute from that, from the generating function, we can obtain a bound on the CCDF in this case.
So here, y
right?
is an integer?
And y is, no, not necessarily.
And what is it?
Just 1 second, let me see. Y. Yes, because we are assuming, you know, so this is flow. Yeah. Yes, it's fluid flow, but it's per bit. Y is bit in bits. Yes. Y is integer.
Y can take values.
it will be here. I mean, when y increases, this will reduce it. Basically, this will take it. You know, so this goes up and this goes down. So this goes faster down than this. So then it will converge. Yeah.
Good. Thank you.
Thank you.